I will start recording and share the screen. Are there any questions for me about anything? Okay. Oh yes, so there is some work going on in my building, and because of that there is noise and there may be interruptions. So today I'm using a headset to try to minimize the noise. Can you hear me okay now? Can somebody confirm that you can hear me okay?
Yes, we can.
Yes,
We can
we
hear
can hear
you.
you.
There's no noise.
Okay. Okay, great.
I have one question. When is the midterm? And up.
Yeah, the midterm is going to be on the Monday after 3 weeks, of course, and the final is going to be on the last day, which is also Monday, I believe. It will be during the regular class time. Okay. So we're just doing 2 even parts. Okay, so we have the spinning wheel and we're going to start the lecture. Okay, so let's go over the homework. The first one is the independent switches, right? And we're going to start with the 4D cube. Again, I'm not running my video, I'm just sharing the screen to save bandwidth. Right, so here we have what we call a two-dimensional cube. I'm sorry, a one-dimensional cube, which is just a line from 0 to 1. Quick question, what would be a zero-dimensional cube? Who can tell me? Quickly.
A
Right,
point?
if this, just
Just a
one point,
point.
right? A zero-dimensional cube would be just a point or a single variable, you know, literally a single switch that can be 1 or 0. Right, two-dimensional cube, we have 2 switches. I'm sorry, one-dimensional cube, we have 2 switches. Now we're going to make it into a two-dimensional cube, which is a square, and this has 3 switches. I'm sorry. That's right. And now we're okay. I'm sorry. This has 2. Okay, I misspoke. So the one dimension. Okay, so we'll just do what we're doing here. Okay, this is the two-dimensional cube where we extruded the single line, and now we have 2 dimensions, switch 1 and switch 2, right? With one-dimensional cube, we just had 1 switch. Okay. With zero-dimensional cube, we had nothing. Okay, so here we now projected the square at the distance 1. And now we have a regular 3-dimensional cube, and we have 3 switches represented by 3 dimensions in this coordinate space. Okay. This is our 3D cube. To do a 4D cube, we will need to basically take the whole cube and project it into the 4th dimension, right? So the first 3D cube is made up of blue and green lines here. And when we project a second copy of it, it's in red. And we also connect in red all of the new vertices to all of the vertices of the old cube, that correspond to each other. And of course, in 4 dimensions, all of these angles are going to be 90-degree angles. Okay, and that allows us to have 4 dimensions and 4 independent switches. Any questions about this? Okay.
Sorry, Professor, I have a quick
Yep.
question.
Yes.
Is it okay if my homework looks a little bit different than yours? Because some of the points are just shifted in a different direction. Like I think yours is like 90 degrees rotated than mine. I don't know how to explain it, but
No, you explain perfectly. Yeah, that's absolutely fine, right? We're making a 2-dimensional representation of a 4-dimensional structure. It's not going to be, there are many ways to do it, of course, no problem. Okay, so now let's continue solution with the truth table. This is going to be a little bit more straightforward. So 4 switches simply means that there are 4 input variables. And here we have them. And here they are arranged in a way that all of the states, go from the smallest binary number to effectively the largest binary number, but really it doesn't have to be that way, right? So a good way to do it exhaustively is to have the first variable, we have all zeros, then all ones, the second variable, zeros, ones, and et cetera, et cetera. So we have 4 variables, and this is the complete truth table from. Right? And then now we can see, right, if all switches are off, then the first version of this Boolean function, we're going to start it at off, right? When we flip only one switch, it goes to on. Again, these are not chronological. We can, rearrange them, and it will just change the result. But what we care about is a transition from a state to state, yeah? So if we were transition from the second to the third state, we need to flip one switch and then the second switch. It's going to be 2 flips. That would bring us back to 1. Then here we'd have a single flip and the least significant bit that takes us to 0. Oh, and then, it just continues, right? So whatever the distance is. And of course, let's say, is it always true that transition from 2 to 3, for example, took only 2 flips of switches? Can somebody say, or could it have been a different number of flips? Anyone? It could have been any number of flips, as long as it's even, right? And we flipped it back, right? So yes, we have to have at least 2 flips, but we could also take that most significant 0 and like flip it back and forth as many times as we want, as long as it goes back to 0 in the end. Yeah. Okay. Other questions about this? So then we have the second Boolean function that assumes that in the initial state, where all switches were off, the lamp was on, right? And then this second Boolean function is going to be the perfect complement of the first one. Okay. I don't know why I didn't go by 1. Anyway, okay. Next, we're going to write all axioms for the Boolean algebra. We'll abbreviate it from now on as BA, of the power set of sets, right? Where set itself is not an empty set, right? Not equal to empty set.
Say, Professor, I had a question.
Yeah.
What's that third symbol with the loop and the hook?
Yeah, that's the complement symbol, right?
Okay.
Some people say that it looks like E, but it's supposed to look like a fancy C, right?
Okay.
So in the okay, so it's the complement symbol. Very good.
Thank you.
So we have P, which is the power set of S. Then we have the union, the intersection, the complement, the null set, and the set itself, right? Where power set is a set of all subsets of S. Okay. So this is subset. So here's the solution. So we have the set, we have the call set B, then we have, this is another sign for complement, right? The apostrophe, or it could be a horizontal bar over the whatever is being complemented, right? It's the same as complement. And then we have the 2 possible values, 0 and 1. I mean, the 2 identity values. Okay. And then here we have our, right, so this is the way we saw it before. And now we're going to figure out to notate the same, to express the same idea in the set theory. Okay. So or and are closed operations in this set, meaning that If x and y are part of the set, then x or y will also be part of the same set. And again, x and y is also going to be part of the same set for all x and y's that are part of set itself. OK, so now we're going to express it using union intersection. So we will say that instead of or and, union and intersection are closed in the power set of S. So X union Y is a subset of S, and it's the same as the part of the power set of S, right? And then X intersection Y is a subset of S for all X and Y that are subset of S. So do note that X, if X is a part of the power set, it's the same to say that if X is, let's say, part of a subset, it's also part of the power set, right? Because power set is set of all subsets. Okay. Now we have the identity elements, 0 and 1. So 0 is the identity element for OR, and 1 is the identity element for 1, right? For all x's that are part of set B. As a union intersection, right? So here we have the union of X and null set. It's the same as union of null set and X, right? That's commutative. And what is the union of null set and X? Who can tell me? It's X itself, right? It's X plus null set, and null set is nothing, right? So here we have null set as the identity element for union. And now we're going to find the identity element, or prove that the whole set S is the identity element for intersection, which is the counterpart of and, right? So X and the whole set, right, is the same as whole set, well, and X, or let's say intersection of X and whole set is the same as intersection of set, whole set, and X. And it is X, right? Because if you do like the Venn diagram, then X is going to be inside S, right? But the intersection is only where we have both of them, which is X itself, right? For all X's that are subset of S in the subset S. Okay. Now we're going to translate commutativity, right? So X or Y is the same as Y or X. We'll do that first. So here we have it. X union Y is the same as Y union X. And then the second commutative rule is that X and Y are the same as Y and X for all X's and Y's in B. So here we have the set version of this is X intersection Y is the same as Y intersection X for all X's and Y's in the subset S. Okay, now
Professor,
the distributive rule. Yes.
Hi, Guy here. You seem to be distinguishing between the plus symbol and the union symbol and the dot symbol and the intersection when I think they're the same. Is that right? Or
well, yes, they are the same, and that's why we can translate it. Absolutely, yes. The meaning is, it's just that we're expressing it, on the left, it's, the way I showed you in the Boolean algebra notation, and on the right, it's in the set theory notation. But yes, it's.
Oh, I see. So you use the U or the cap and cup for set theory, and the plus and dot for binary.
By Boolean algebra, yes.
Okay.
Yeah. So the whole point of this is to show that yes, the meaning is the same. Okay. So the distributive property, right here we have X or Y and Z are the same as X and Z or Y and Z. So let's look at that first. So here we have it, x union y intersection with z is the same as x intersection with z union y intersection with z, right? So it's really almost as simple as simply substituting the two, or for union and for intersection. And here we have x and y or z is the same as x or z and y or z. And then in set theory notation, it's going to be x union y intersect z is the same as x union z intersect y union z. Okay. And then 5, right? We have the complement. So x or complement of x is 1. So let's see that. So here we have, oh, excuse me. We're going to silence that. We're going to, excuse me. Okay. All right. Yeah, I apologize. So here we have for all x's in the subset, a complement x is also in the subset, and it's complement of x such that x union complement of x is the whole set, right? So we have the whole set, then x is a part of it, and then the rest of it, and if we union with not x is going to make the whole set. And then if they don't overlap at all, so the intersection of x and complement of x is null set. And the last one, we have that in our Boolean algebra, we need to have at least 2 elements. That's what we usually do. And they're separate from each other, right? So 0 is not equal to 1. And then, again, there are at least 2 elements in the set notation where we have the full set and the null set, and they're not equal to each other. Right, so that means that in the set theory, in order for it to work, you cannot have an empty set. You need to have at least 1 element in the set. Not remind me, I'm asking you, what is the number of subsets in a power set? I'm sorry, what is the number of sets? Yeah, subsets in a power set in a set, stemming from one set. What is the, so let's say that I have just 1 element in a set, right? The minimum required. If I have just 1 element in the set, how many subsets will I have in a power set? Who can tell me?
Be 2.
Yeah, 2.
What is it again?
2.
It will be 2. That is correct. But how did you get from 1 to 2?
Well, there'll be the null set and the element itself.
That is correct. But how? Like, what is the universal formula? Let's say that we had. One more time.
2 to the n.
That's right. 2 to the power of n. Yeah. So, for example, in the sort of like the most trivial version of this, when we have only a 1 or null set, right, or sort of like just 1 element, then we can have an empty set or a full set, right, which is 2 to the power of 1. Okay. So here we have, we're going to write the axioms of the Boolean algebra. Oh, I did that already. I'm sorry. I need to just go through. How do I... No. So there doesn't seem to be a way to quickly go through this. Okay. Right. So now let's look at some of these using Venn diagrams, right? So here we have union of x and y intersecting with z. We want to prove the equality that is the same as x intersect z. I'm sorry, the intersection of, yes, x and z union with intersection of y with z, right? So we're going to look first at the left side, right? So I just copied the left side down, and then later we'll look at the right side, right? So, okay, so what do we have here? We have union of x and y, right? So let's say that x and y overlap a little bit, but their union is going to be this whole upper area, right? The two overlapping white circles, okay? And, stop me if it becomes unclear. And then when I intersect that with z, right? So here we have a z that partially overlaps it. And we are going to take the top, right, which is union of x and y, and only the part of it, right, that intersects with z is going to be, it's that little thing in the middle, right, that is going to represent the result of that. Right? So now we're going to do the right side. For the right side, we have x union z, it's these two circles together. And then we have y union z, these circles together. And we do the intersection of them, right? And the result is the same in this. Okay. Right, so I may have misspoke here, right? So, but anyway, so this is it. Sorry. It's the noises here substantial, but I'm glad that you're not hearing it through the headphones. So left side is equal to right side. Okay, the next one is 5, and this is the complement. So if x is this white circle, is part of the set, then then the complement of x is going to be the rest of the set. So if we do the union of them right, together, then it's going to be the whole thing. But if we do the intersection, then it will be nothing, right? Empty set, because they don't overlap at all. Any questions? Okay. So you will probably like it. So this is part of the homework for today, but I realized that was a lot. So if you weren't able to finish this part for today, you can finish it, you can submit it as the homework for tomorrow, and then I will assign something else too. And I'm going to sort of give you, okay. And so again, if, I apologize. If you didn't do that part for today, you can do it for tomorrow. Okay, so now let's look at this theorem. Every Boolean algebra is equivalent to Boolean algebra over power set for some set that is not empty. Size of any Boolean algebra has to be 2 to the power k for some k that is greater than 0. Could be at least 1, but no less than that, where k is the size of the set. Okay, for which we take the power set that is the Boolean algebra. So here we have the principle of duality, which is very important, is that if we have a true statement, if we can replace the or by the and or backwards and replace at the same time, swap zeros for ones or the other way around, and we will obtain another true statement, right? So that's the principle of duality. So next, for any Boolean algebra, and here we have it, is the sextuple, right? The set, the two operations, the two binary operations, the one unary operation, and two identity elements, okay? Where we know that the axioms 1 through 6 hold. Now we're going to prove the properties, try to prove the properties, which are 7 to 12, right, on that page that I told you to print out. Okay, so here we have 2, 4, and 5. And we're going to try to prove the properties, right? So the first property is property number 7. And we're going to try to prove that OR and are idempotent, right? Or effectively, what it means is that X or X is still X, and X and X is still X for all X's in the set, right? So that's the idempotency. So by duality, we only need to prove just one of these two qualities above. But, so using the second axiom, right? And this is how, like when you're doing your own proofs, this is what I want you to do. Over the equality, when you're doing translation, you should put in the little number in parentheses, and that will tell me what axiom you're using to support your proof. Right? Because of identity element axiom, X is the same as X or 0, right? So we're unfolding X effectively. And then because of the complementarity, we can say that we're going to unfold 0, right? We're going to say the 0 is the same as X and complement of X. Any questions about this moment? Right, so it seems that we just started with X and we're just continuously unfolding it, but we can do that, right? Again, any questions about these two transitions? Okay, no questions. So then we're going to use the fourth axiom, the distributive one, and we're going to, convert this, X and X or X to X or X and X or X prime, complement of X. Right? And now again, using complementarity further, we can say for sure that X or X prime is always going to be true. So it's 1, right? So X or complement of X is 1. Again, if there's a question, immediately tell me. Right, and that's the coefficient, and that's the end to the what's in the first parentheses, X or X. Okay. And we're done, right? We've proven we started with X, we started with the right side, and there we have it. Right, so again, using the second axiom, we go from that to X plus X. Any questions? All right, so that was idempotency. Now let's try to prove the dual equality. We're a dual proof, right? So I told you that if one of them is true, the second one will also have to be true. But now let's just do it independently and sort of like prove that, right? We'll do the second one again. We'll prove that it's true, and then that will also prove the duality. Okay. So, right, it's not needed, but we're just doing it as an exercise to see duality in action. Okay, so we start with the X again. We're going to use the second axiom to unfold it into X and 1, same thing. Then we're going to use the fifth axiom, the complementarity, to unfold the 1 into X or complement of X. Right? Then we're using, again, the distributive axiom to convert that into X and X or X and complement of X. right? Then using, again, complementarity axiom, we will see that x and complement of x are, of course, mutually exclusive, so they're 0, right? And what is left is x and x. And then again, using the identity axiom, we can get rid of the 0, and we have left x and x. So we've proven the second idempotency equation or equality, and also by virtue of that, we've proven the duality here too. Okay. So this is the new assignment for tomorrow, where you will have to prove the remaining properties, right? So here we've proven 7. You have to prove A12 using axioms 1 through 6. And you can use the 7th property also. So you can rely on this property that we just proved here, the idempotency, to prove the other 5 properties. And also, if there are multiple proof possible, you only have to provide one, right? You don't have to do it the way I did it here. Any questions about that for the homework? Okay. Right. Now we're going to just do a bunch of exercises together, so that it becomes more intuitive for us. All right, so we start with x and y, or x and complement of y. All right, so now we're going to convert it to x and y or complement of y. So y or complement of y. Right, so we use the 4th axiom there, and then y and or complement of y is the whole set, so it's 1. Yeah? So we use that using, we prove that, we show that using the 5th axiom, and then using the 2nd axiom, we get to just x, right? So we were able to simplify that long expression into just x. Next, we have x or y and x or y complement. So using the 4th axiom, we can go from this to x or y and y complement. Then now we're going to convert y and y complement to 0 using the 5th axiom, and what we have left is just x using the identity. I'm sorry, using the identity axiom. Okay. Now the next exercise, we have z and x, or z and complement of x and y. And because of commutativity, the order there is not doesn't matter. Okay. So that is the same as z and x or x complement and y, right? That's using the 4th axiom. Then again, using the 4th axiom, we can we keep the z, and we can convert x or x complement and y to x or x complement and x or y. Right? Now these 3 elements, right, they're connected by the and, the 2 in parentheses and the z. Okay, so x or complement of x is 1. Yeah. So then that 1 can go away. We can just say z and x or y. And that's all. That's as far as we can simplify it. Okay, next one, we have x or y together complement, and x complement or y complement complement, right? So we'll have some double complements here. We're going to use De Morgan's law, which is it's not one of the axioms, one of the properties. Okay. So using the De Morgan's law, 10, right? So as we go ahead, with the proofs of things, you can use numbers from 1 through 12, right? The first are 6 axioms, and the second 6 are the properties. And even though in some other textbooks or maybe some other people's lectures, they're slightly different, we're just going to use the ones that I'm teaching you here, and our textbook has them too. Okay, so because of De Morgan's law, and right, because of the double complementarity property, so the complement of x is the same as x itself, right? So because of those two properties, we can say that, so De Morgan's law, we can say that x complement and y complement and x and y, right? So for shorthand, when you see two elements next to each other, the dot is implied, the and is implied, okay? So I guess for clarity, I should have put in the dot everywhere, but I don't. So in many slides, you'll see and omitted the logical multiplication, but it's there. Okay. Now, using the third axiom and the fifth axiom, right, what we have here, it would be clearer if we switch the order, which you can because of commutativity. What you have is x complement and x, and y complement and y, right? So what is x complement and x? Anyone? What is x complement and x? Just by itself. Right?
0.
It's 0, right? It's the intersection, if we look at it as sets, it's the intersection of two unions that don't overlap explicitly, right? So, and the same thing is true for y complement and y, right? 0 again. So we have 0 and 0, obviously 0. So that was a great simplification. Okay, so now we're going to do a proof of a more complicated equation. So let's look at the left side only for now, right? It's long enough. We have x and y and z, or x complement and y complement and z, or x complement and y and z, or x and y and z complement, or x complement and y complement and z complement. Okay. So let's break them up into sort of couples that are going to be useful to us. So we're going to couple x, y, z with, x and y and z with x and y and z complement, okay? And we're going to sort of couple together x complement and y complement and z with x complement and y complement and z complement, right? So in these pairs, there is only one element difference. And then we have one that is sort of left an orphan term here. So this is the wiggly cyan line. Well, for it, we can use the x and y and z twice, right? Why can we do that? Who can tell me? Right? Because whatever the element is, we can say that that element or itself, it's the same thing. It's still that element, right? It's just the element is big. It's x and y and z. Right? It's the idempotency. That's the one that we showed in the previous slides. Okay. Right, so you can do this kind of thing with the numerical algebra, but with Boolean you can. Right, so here I have it. I have instead of just x and y and z, it's the same as x and y and z or x and y and z, right? Is this clear to everybody? Right, so we can play these sleights of hand.
Sorry, can you repeat that?
Yeah, I was going to ask that as well.
Okay, so let's think of it in terms of sets, right? Imagine you have the whole set, and inside it, let's say it's just the x, right? So if I say x or x, what will it be? Will it
Just
still be the
X.
same? It will still be x, yeah. And idempotency goes both ways. I could say, what is x and x? What is that going to be?
So just X.
It's still just x, right? So that's the idempotency property, and because of that, in these equations, we can just like sort of make things out of thin air, as it were. Does this make sense?
Yeah, that makes sense now. Thank you.
Okay.
Yes,
Good.
thank you.
But how do we know
Okay.
to do that for that specific?
Well, that's the trick, right? We did it here because we were able to find like good couples, and then we had this orphan, and there was no couple for it, so we just made it one. Or I mean, you can't always do that, but in this case, we were able to do that. Okay, so now that we've duplicated x and y and z, now we can have a pair for each of them, right? And here I have them underlined. And right, and again, this idempotency property is property number 7, and you can just go to the previous slide and it's there. Okay, now using the fourth axiom, we're going to grab these couples, right, and convert them, right? So x and y and z, or x and y and z complement, is the same as x and y and z or z complement, right? So now we can, and then we can do the same thing for 3 other pairs, right? So we did the same thing. Now, when we look inside the parentheses, what do we see there? We have z or z complement, and then we have x or x complement, and then here we have again z or z complement. So what do they all end up being, these 3 expressions in the parentheses? Quickly.
1.
1, right? They're all 1, right? So something and the or the complement of it, or the complement of itself is the whole thing. It's the whole set, so it's 1. Exactly right. So that's our 5th axiom. And that simply means that what we have is x and y and 1, or 1 and y and z, or complement of x and complement of y and 1, right? And then using the second axiom, we can just get rid of the 1, and we have x and y, or y and z, or x complement and y complement. Okay. So now we can look at the right side, and we got it, right? In slightly different order, but that's okay, right? We have x and y, or x complement and y complement, or y and z, and we're done. And let's hear some questions, and beyond that, I'm going to finish early today, because even though I'm glad that you're not hearing it, there is work and there is a lot of noise, and I'm distracted because of that. But I think this would be a good sort of like place to stop. But before I let you go, I would like to hear some questions.
So I have a question. How often are we going to be asked to like write our own proofs for like the exams?
Okay, could you please repeat your question?
How often do we have to write proofs for the exams that we're going to have?
So there will be 2 exams.
Yeah, so is it like we're gonna have like one proof, or do you know how many, or just for each of
Well,
them?
the exams are going to be, 1 hour and 30 minutes, so they're 90-minute exams. So you'll have enough, for 90 minutes. Now, of course, because of our remote learning, these exams are going to be, open book. But yeah, that's, and they're going to be, the same size. The amount of material will be covered, will be the same, but it will be all different materials. So it'll be as if you're taking two courses, like uh, architecture 0.5 and architecture, second 0.5, right? So the first exam will cover the first 50% of the course. The second exam will cover the second 50% of the course, and they will count the same. Actually, let's confirm that that's what I put in the syllabus.
I don't think that's what he's asking. I think he wants to know how often are we like doing proofs in this course? Like,
Oh, often. Yeah, absolutely. Yeah, I mean, I will probably have some multiple choice questions too, but even in the multiple choice questions, you will have to make the conversions on like scratch paper, right? And then, you'll be able to pick the multiple choice, and then you'll have to, on the exam, take a picture of all of your scratch paper and submit it to. Did that, did that answer the question?
Yeah, thank you.
Okay, okay. So let's confirm that that's what we have in the syllabus. Right, exams are the same. And actually, I'm going to sort of change that somehow where the quizzes and the homeworks are sort of like extra. So, which means that probably the weights of the exams will be increased a little, but they're the same between the two exams. Okay, good. Also, let me point out that in addition to giving you extension on yesterday's homework, there is new homework, right? So let's see. So that's the repeat. Right, so this is the repeat of previous. And I also assigned 6.2. Why don't we see it? Oh, there it is. So in the slide 8 at the bottom, right, you have the new homework, and that is also due tomorrow. All right, questions?
so wait, is it just this one at the bottom, slide 8?
That's correct, right? That is, so you will have the opportunity to, submit that part of yesterday's homework if you haven't submitted it already. If you already submitted, don't worry about it. Then you have literally one thing tomorrow. Yep.
Are we allowed to resubmit?
Yes, you can resubmit. What you can do is what you submitted yesterday, you're not perfectly happy with it, you can submit it today also. And I look only at the latest one. Okay?
I mean, yesterday's homework, are you talking about like for not just the axioms, like the
Well, no, the proofs of the six properties, right? It's the numbers 7 through 12. I assigned it for today, but I'm just giving you, that will not always that will not often happen. I'm just giving you. I mean, I feel like that was a lot. And I'm assigning less of the new stuff today. I did want to start assigning a lot from the very beginning so that you kind of get into the habit of doing it right away. But right now it's going a little bit easier. And maybe I'll go harder again next week. We'll see. So how about questions about material? So everything is pretty good, right? If you're comfortable with set theory, it's really not that hard. Okay. Right, so if there are no more questions, then I'm going to let you go now. I hope that the work that they're doing in the building will be done by tomorrow, and then.
Are you gonna upload the homework questions soon?
Which?
The,
The one in,
on the slide.
Oh, yes.
Yeah. Okay.
Yeah, you know what? Yeah, I'm so that let's just make sure that I'm going to do it as soon as I sign off, right? So I'm going to post the slides for today, right? So you can right away, you'll be able to right away just download the 9 slides for today. And in slide 8, you'll see the homework, and then I also will create a submission link and post it on the homework page. Any questions? Any questions about this last problem? No. Okay. Anybody needs to talk to me in terms of office hours? No. Okay, great. So you can go out, enjoy the summer for an hour, and then you have to go back to your everything else that you have to be working on. Okay, I will see everybody tomorrow.
Professor, I just
Yes?
want to remind you to stop recording because you sometimes like have really long recordings.
Okay, I'm going to